Right, ladies and gentlemen, it is November 9th. A lot of us were awake quite late last night. So I do have a couple of things to say since I said something to you on November 7th, which is that if you went out and exercised your right to vote, thank you. Because it matters for a reason that I hope I can make a little more clear later. The one thing to keep in mind is if you don't like the result of the election, it is better to have governments elected democratically than in any other way. Trust me, from other places in the world, this is very, very clear. And whether you believe in democracy is really tested when you get a government that you don't like. So, the people spoke, and we have a government. We've had governments before, some we've liked, some we haven't liked. It's a cycle. There is nothing especially amazing about this cycle other than we've got something called the internet, and everybody's basest thoughts are out there in public for everybody to see. This is not to do with this particular election cycle. It's to do with the internet. So, it's a little... some of us are disappointed. I'll say quite frankly, I am disappointed. But, we've come out of this before, and we will come out of it again. I will say something for myself personally, and now I'm speaking just for me. I'm not saying that this is what you ought to do or that this is what the university feels or anything like that. This is just me. I'm somebody you've known now for about 11 weeks. So, I sat and thought yesterday about, so what is it that I now do? And the one thing that is clear is that the country is divided. And that is why I thank you for having gone out and voted, even if the vote didn't come out your way. Because when you vote and the vote doesn't come out your way, it's still recognized that there were these people who thought differently. Right? And that is very, very important, especially in this election when the result, I don't know if you've been looking at any of the discussions, but there is one variable that seems to be quite is quite important for predicting behavior, and that is higher education. The college-educated behaved one way, and those without college education behaved another way. And so this is something that we need to look at quite hard. You know that it is tempting to conclude causation. But you know that you shouldn't conclude causation. You've just done a project. You shouldn't conclude causation. In fact, did I pick up the... That. Do you remember seeing that? So if you run your inference techniques at the time when the executions were suspended, it sure looks like the murder rates went up. And then if you look at the inference techniques once again, when the executions were reinstated, it sure looks like the murder rates came back down. But then there's that. Right? Whether it's a death penalty state or a non-death penalty state, the rates are going up and down essentially in parallel. This one, the solid line is Canada. And to this day, I haven't seen a decent explanation of why those graphs are going up and down the way they are. You did notice, right, the second y-axis here? Was that not part of the project? Yes? No? Did you turn in a project yesterday? Maybe your partner did that part. But there are two vertical axes on this graph. And maybe, since people are looking at me with such surprise, I'll let you look at that. There are two vertical axes on that graph with different numbers. There's a way not to draw a graph. What they wanted to say was that the rates are going up and down at the same times, but they kind of overstated it as though the graphs are completely parallel. They're not. They're not going up and down by the same amounts. But they switched the vertical axis on the right-hand side to make it look like the vertical distances are the same. It's not like that. But the fact is that rates are going up and down at the same time epochs, whether you're in the United States or whether you're in Canada, whether there is death penalty or not. So in other words, the world is far more complicated than one variable. And so that college education separates voters is an observed fact, but what it is an association. Why it separates voters is not yet clear, and I think it deserves quite a lot of study. Because we have free high school education in this country, but college education is still out of the reach of many people. And that, I think, as educators, we do need to look at. And I don't think anyone has the answers yet. I mean, maybe college education does change minds, but also maybe because you have a college education, you have a certain kind of job, and so you feel more secure in your future than if you don't have that kind of job. Or maybe you don't have a college education because based on your background, you couldn't afford it in the first place. Right? So there are many related variables, and we have to look very carefully. The polls did not have an answer, and the polls did not have an answer. It's very clear why they did not have an answer, I think, because the numbers are very close. The percents were very close. And if you looked at polling results, people trumpeting, so-and-so is ahead because it's 44% to 42%. You guys know there is something called a margin of error. And when the numbers are so close, you're within sampling variability. And in a much more complex way, this is one of the points that Nate Silver was trying to make. His model is more complicated than anybody understands, other than him, I think. But the fact is, when numbers are so close and they're based on random sampling, you actually don't know what the answer is. And the reality came out always a certain way, or almost always a certain way, and that's why the polls had a problem. Polls have difficulty predicting close races because of the plus-minus. And also, polls just have difficulty in general now. The polling organizations were great when there was a fixed way of reaching people. There were home addresses and there were landline phone numbers with phone books, right? So you had a method of randomization and you could get people to pick up the phone. But now, there is a big fraction of the population that just doesn't have a landline phone. They have cell phones, and everything's blocked except their significant other. And so, it is hard to reach what is called a representative cross-section of people, and so the polls had difficulty. But anyway, the world is the way it is. We have had many different kinds of governments. This is not uniquely awful or uniquely wonderful. 4 years from now, actually 3 years from now, this whole circus is going to start again. Most of you will have graduated. Just think about that. You'll be out doing wonderful things. You will. You will. I am still going to be here, talking to the next set that looks like you. I hope I'm still going to be here, talking to the next set that looks like you, and they're going to be as wonderful as you. Possibly I have a few graduate students in the room, and possibly they might still be here, if not in this room, writing it up. That takes forever. But most of you will have moved on. The world will have moved on. That dugong that we saw the other day will be swimming around. We're going to be okay. The thing is to do what I will be looking at for myself, and this is again me speaking for myself, not for the university, is I will be looking at the freedom of the press to do my part to ensure that journalists are not under threat. And I will be looking at what I consider makes this country really uniquely wonderful, is that the founders wrote down that we are all equal. And that people should be treated in that way. I have to take that on me. I mean, as an individual, I can't expect the government to do that. I can't expect political parties to do that. I have to take that on me. So if I see... So first I have to not engage in that. I will not engage in vilifying, ridiculing. A lot of that has happened, and it doesn't have a good effect. And I will, if I see that people are being certainly vilified or ridiculed, but even diminished, for some reason that has to do with their birth or their family background, like their ethnicity, or their gender, or their gender identification, or their religion, or whether their family was immigrants, if that is happening, it's not enough for me to do what I've been doing thus far, which is I've been spluttering at the TV. I've been going, I can't believe people are like this. It's not enough. It's not enough for me to be talking to my colleagues at Berkeley saying, can you believe this? Because everybody at Berkeley thinks the same way anyway. So that is not helpful. And that is what we have been comfortably doing, my colleagues and I and other people, in our own beautiful little worlds. But there's another world. And the two worlds have to talk to each other. And we have not done that, and that needs to happen. And so that's, my goal for the next 4 years is to not expect other people to do that for me, but to see what I can do for myself. What can I do for myself? I have no clue. It's 5 minutes since the election. But that's my gut instinct. All right, we got to work. So thank you for submitting the project. It is a normal week, except that it's not a normal week. Friday is a holiday, and we could all use it. I hope you will find somewhere. By the way, if it's all too painful, apparently we can now all smoke. Something worked. All right, look. In any analysis, multiple variables are involved. Trying to predict one variable based on multiple variables is complicated. You can see that a lot of very expert people had a great deal of difficulty. What we are trying to do in this class is to give you good ways of predicting one variable based on a single variable. As you go further, you will learn to draw in more variables. So in particular, Stat 28, that is being offered next term, does exactly that. How to use multiple variables in your analysis, but we are going to stick to one single variable. And what we have done is we have said, given the value of one variable, I know how to use a straight line or sometimes a curve to estimate another. And today I want to examine that in the context of random sampling. So thus far, our data have been so we had one set of data that was all the hybrid cars that had been manufactured, all the different makes and models up to 2013. That is not a random sample from anywhere. That was the population. However, Galton's 934 people with their heights, well, there were 934 out of some population. We have had a genuinely taken random sample of mothers and babies, and we had variables that we measured on those. Now, if we look at relations there, we might see linear association or straight lines, and we might make predictions, but the question always arises, is that something we're seeing by chance in the sample, or does that actually reflect something that is the truth? And for this, we need to be able to say what we believe was the sampling process. And so a very commonly used regression model says the following. That you have two variables, and I want you to, for the beginning, just think of babies, think of the number of gestational days, how long they've been in the womb, and the birth weight, these two. A model might say that these two are linearly related, but we never get to see the line. What happens is, at any number of gestational days, that's the point of the line, that's the truth, but we see that contaminated by an error. And so we see this point, and so on. And the errors are, now I want you to take a look at that detail. The errors are drawn with replacement. That means if you know one error, if you see one error, it does not affect the other. From the same distribution. From which distribution? A normal distribution centered at 0. What does that mean? That means you're as likely to be plus or minus. Yep. And it's the same normal distribution for all the errors. What does that mean? That means the errors are as likely to be big or small regardless of where the x is. So your scatter diagram should look like what? It should look like points that have been pushed off a straight line. So it should go up linearly. Yep. If it waves, something weird is happening. So you go up linearly, and it should go up. The vertical spread should be about the same throughout in the bulk of the data. That's what this model predicts your data should look like. And in fact, of course, we don't get to see the truth, we get to see that. And so now we have to figure out, well, what should we use as our predictions? And so we know what to use as our predictions because we know how to do, I'll remind you of these data because you haven't seen them for a while. Okay, so we have 1,100, a random sample of size 1,174 and a bunch of variables measured on these mothers and their babies. And what we're going to do is look to see whether we want to estimate, whether we want to use the regression model. And I look at that, and it's not perfect. These few points are giving me a bit of grief. But it's not terrible. You have some sense that, okay, they're kind of above and below the line about equally, and outside, in the rare places, you will get weird data because you don't have enough data actually to see exactly what is going on outside. And the correlation is that. And so now there's the question of how we should go about making predictions. So if somebody tells me the baby's at 300 gestational days, my prediction of birth weight is going to be right there. You agree? Is that it? Am I done? Is that the accurate prediction? In what way could it be off? Why could it be off at all? So this is the thing to now be very clear about. Why could that prediction be off? What does our model say? Our model said there's some true line. Yep? Is that the yellow line? It is not the yellow line. You never get to see the true line. Yep? You saw one set of 1,174 points, and those points have your regression line through them, but that need not be the true line. The true line might be somewhere else, right? And so what you need to do is to figure out what is the relation between our line and the true line. Let me just see if I drew. Yeah, okay. So I want to do a little I'm going to run the code. I'm going to write the code and tell you what it's doing. This is a function that I wrote to show you something. I'm going to give it a slope. How about I give it a slope of 5, an intercept of -10, and a number of points. Okay, I'm just going to do something here. Okay. So what this function does is it produces a bunch of graphs. The first thing it does is it does what the model says. The true line is determined by this slope and intercept, right? I'm just pretending that I know everything, right? So I just determine a true line, and I ask for 25 points to be generated. So the true line is first drawn, and then at 25 values of x, actually let me show you 10, because that might be easier. At 10 values of x, there are normal errors that have been found, and the points have been jittered off the line. Okay? So here is the reality that we get to see. We get to see the exact same points, but without that green line. Right? And we're trying to figure out where was that green line. So what are we going to do? We're going to put a regression line through that. Right? So that's what we do. That's our regression line. That's our best fit line that we spent the last couple of weeks developing. Okay? But now there's the true line, and what I've done in the next plot, because right now we are pretending that we know everything, is that we brought the true line back. The yellow line was our estimate. The green line was that original true line. Take a look. Close or different? Yeah, close-ish. Yep. If you run it again, there's a true line, there's another set of 10 points, there's my regression line, the gold one, and there's the green line. Gold one is not that far from the green line. I'm trying to get it to be far, but it's out of my control. It's however the lines are being generated. So here we go. Right, so what you're seeing is that our method isn't bad. If the model holds, our regression line comes reasonably close to the actual line. And if the sample size is large, I've got only 10 points. Let's do 100. Actually, before I do 100, can I just leave this up here and ask you if there are questions about what you're seeing? What that is a simulation of the model and then a comparison of how our regression line does as an estimate of the true line. Yes?
I'm not entirely sure how the green line is being drawn. Is it putting random errors?
Yeah, so the green line is being drawn. The green line, you see, the green line is 5x minus 10, right? So the green line is something that I have said has to be the true line. The points are generated by taking an x and then adding random errors. Right? That's what the model says. Draw one line, go to your x's, and then add normal errors. So that first picture is generate the points. The second picture is show us just the signal plus the noise. Neither the signal nor the noise, but the sum. The third picture is our attempt to extract the signal. And the fourth picture is a comparison with that attempt and the signal itself. More questions? All right. So if you increase the sample size, exact same line, you've now generated 100 points. That's the scatter you get to see. That's our yellow line is the regression line through that exact same scatter. And there's our regression line and the true line. And you have this in your textbook, you can run this over and over again with different slopes and intercepts and changing the number of points, and you will see that for a large number of points, our regression line gets really quite close. So it's a good way to estimate. And so if we go back to our diagram here, this is a decent estimate of the regression line. However, it is not exactly the regression line. So if I want to, from this, identify the regression line, I have to identify a slope and an intercept. Do you agree? I have to find the true slope and I have to find the true intercept. Now, the true slope, I think, should be close to the slope of this one. And what is the slope of this one? We have a function that does that. So the slope of this one is about 0.7, ounces per day. Great. So the true slope should be around there, but it's not going to be exactly there. It's going to be off by a certain amount, right? So how do I figure out how much variability there is in the slope? Bootstrap? Question mark? Yeah, we will delete the question mark. So remember when we were trying to estimate a population median? We had our sample. We got one median from that. Right? But then we said the sample could have come out differently. And that would have got a different median. How did we create a different sample? We bootstrapped our own. We didn't have the resources to go out and collect another sample, so we took our our original sample as a stand-in for the population and drew another one. We're just going to do the same thing again. We've got one sample of 1,174 individuals, and, well, actually pairs of individuals. These are mothers and babies. We're just going to take a bootstrap sample from there, and that's going to give us another set of values. And so the next thing that we do is do that. Okay, there's your original sample. I took a bootstrap sample and drew another scatter diagram. Look at the second one. Does it look like the top one? Yeah? Now you have to squint. If you look at it, do you see that it looks a little bit less dense? There's a few more holes. Yes? Why is that? Because we're sampling with replacement, and so we're pulling some of the same points over and over again and some points not at all. Right? So it's a little bit more sparse. Not much. We've got 1,200 points there. But it's a little bit more sparse than the original one. Nevertheless, it looks rather like the original one. So there's one, there's another, and there's another, and there's another. Yep? You agree that through all of these there is a line? You agree that they're all going to be kind of close to the regression line but also slightly different? Yes? You agree they're all going to have a slope? Yep? We can find all the slopes. We can collect all the slopes. We can draw an empirical histogram of all the slopes. Does this feel like been there, done that? Great, the course has done its job. All right, excellent. So I have drawn 4 bootstrap samples, but we can draw thousands of them. Yep? So here's what we're going to do. I'm going to let you read this code. What's going on there? We're creating a bunch of slopes. We start with an empty array. Yep. And we are going to do the same thing. Now, notice the 2,500 times. Normally we have 5,000 and 10,000. I just want to do a bunch of them and not wait till it happens. So I'm just using 2,500. In the book, there are more. Okay, so we are going to do 2,500 times something, and I need to remind you this line right here. Baby.sample produces what? A table. Excellent. Baby.sample with nothing in the parens does what? It samples in what way? With replacement by default, the same number of times as we had rows in that table, right? That is exactly the bootstrap. Now, .sample was written as part of the data science library for teaching data science. And we said, we're going to want a bootstrap. We don't need them to keep entering the sample size and keep entering with replacement. We'll make that the default. So just to save you some labor, .sample was written that way. Okay, so now this is our bootstrap sample, and based on that sample, we compute a slope. Where did this come from, by the way? Slope, table, et cetera, et cetera. What is that? That's a function we wrote quite some time ago. Yep. And so in each of these notebooks, I define the functions at the beginning first. Okay. And then we do what we've done before. We collect the slopes in this array, and then we draw a histogram. We ready? Chugs. That's what the slopes look like. And so if you had to estimate the slope of the true line, what would you do? You would find a 95% confidence interval. That is what you would do, right? You've got a statistic, which is the observed slope. You've got the empirical histogram of that statistic by bootstrapping. You will pick up the 2.5th percentile and the 97.5th percentile, yes? And you'll get an interval. And that is our interval. We are saying it's 0.38 ounces per day to 0.56 ounces per day. The actual one that we got was in the middle there, 0.47 ounces per day. Okay. All right, so what we have done here is called bootstrapping the slope. That is short for bootstrap the sample. From each sample, there is a regression line. Find the slope of that line, collect the whole lot. So we say bootstrapping the scatter, bootstrapping the slope. That's what we've done. So what I'm going to do now is, actually, I'll pause. I'll take questions. Okay, I just want to be clear. There is a parameter that we are trying to estimate. Can we articulate what that parameter is? What is a parameter? It's some number associated with the population, right? Yes? And it's some unknown quantity. What is the unknown quantity that we are trying to estimate? The slope of the true line. Yeah, the green line that we don't get to see. Right? That is an unknown number that we are trying to estimate. One thing to be aware of is that we're never going to know it. We're never going to get to see it. Right? So we're putting a lot of faith in our method here. So there's that unknown number that we're trying to estimate. Our data are generated according to the model, we think. And so then we simply get bootstrap samples and generate our statistic, our estimator over and over again, and pick off the middle 95%. So what I have done here is I have collected all of this, and I just need you to read this part. I'm collecting this method into a function. So I'd like you to please read the definition of the function. All that stuff in green is comments. At this point, you have seen this kind of thing often enough that you can read code pretty much like reading English. All right. This first portion is where the bootstrapping is happening. Yes? Please take a look at that and confirm that it is the same as what we just did before, just with a generic table name and generic column labels and a generic number of repetitions. You agree? So here we collect the slopes. Here we find the middle 95%, the left and right ends. Yep, exactly the same as what we did before. This one is just to see what the slope is of the actual data that we got. It's just handy to have around. It should be somewhere in that interval. I am deliberately not asking you to read all this display stuff because it is all just display stuff. So I will run the definition, and we will... Okay, so now our function is called bootstrap slope. If I run bootstrap slope on my table with the same predictor variable that we just used and the same response that we just used and the same number of repetitions, I should get a clone of what we got before. You agree? I will not get exactly what we got before because of sampling variability, but I should get something that looks pretty darn similar. And this is just a test. The reason I'm running this is just to test whether our function works. While it's running, questions? We done? We're done. The actual slope was about 0.47. That is what we found way early in this lecture. It's the same number. The 95% confidence interval is from about 0.38 to about 0.56. You agree? What did we get the previous time? 0.38 to about 0.56. To the second decimal place, it's about the same. If you sharpen the number of repetitions, that will be more stable. I'm only doing 2,500 repetitions. Yes? The function does not return an object that you can work with. All it does is display. It draws a histogram, and it prints. So if you actually want to work with those numbers, I'll have to edit the function and to have it return the array left, comma, right. Right? All this is display. More questions? All right. And now, of course, once you've automated your method, you can do the same thing on other variables without having to rewrite code. And so what I'd like to do is I'd like to look at the relation between the mother's height and birth weight. Specifically, do taller women produce heavier babies? And that's a natural thing to ask. Scatter diagram looks like that. What do you think about the regression model? Looking okay? Looking terrible? What? What do you think? Does it look linear or not, roughly? Yeah, kind of. Does it look roughly the same above and below? Yeah, kind of. Worth a shot. And, it doesn't get much better than that, right? That those beautiful, perfect footballs, the reason they appear in textbooks is there's one of them, and they appear in all the textbooks. There's always a little judgment to make. Yeah, it's okay. What was the correlation? Not terribly high, about 0.2. But it's positive, it's there. So what we're going to do is we are going to try and figure out what is the slope of the true line. This is a yellow line, but there's a green line underlying this, which I can't see. So what is the slope of the true line? Well, I will bootstrap the slope. We wrote a function to do that. Bootstrap slope, baby. Now the predictor variable is maternal height, the same response variable, the same number of repetitions. I'm going to run this thing while we talk. Questions? You should always draw the scatter diagram before you start talking in detail about slopes and intercepts, right? Because if the scatter diagram was all wavy, I shouldn't be fitting slopes. My program will do it, but it might be a really dumb thing to do. Yeah?
So how does this process deal with the outliers?
How does the process deal with the outliers? This process does not deal with the outliers. When you are running this, you are assuming that the model works. So if you have to deal with outliers, you have to first examine whether you believe the model at all or not. That is a difficult process. Are we done? Yeah, we're done. So what we're saying is that confidence interval runs. So what is this? This is ounces per inch we are predicting, that slope. And the confidence interval says it's about 1 ounce per inch to about 2 ounces per inch. Yep. What was the actual value? About 1.5 ounces per inch. Just almost exactly halfway in between. This is something you've seen over and over and over again. If you believe the regression model and if you have a large sample, then you'll get a distribution that doesn't look as beautifully bell-shaped as what we've seen before because I'm using only 2,500 repetitions. Right? You do more repetitions, it looks better. Questions? Method for estimating the slope of the true line. It's a repetition of methods you've seen before.
What happens when our scatter diagram is clearly nonlinear?
When your scatter diagram is clearly nonlinear, you don't use this model. You need something more complicated. You need nonlinear estimation. Outside the scope of this course, but well within the scope of Stat 28. We showed you how to fit a quadratic, right? So you can fit the function, right? But then errors, well, you could bootstrap the scatter diagram, do it again, and draw an interval. You can. It's the same process. Okay. So what I want to do now is to point out one particular place where a question arises. And for this, the question is, so you see this slope? It looks positive, yeah? The true slope, however, is some different number, and there is always an anxiety. So I will... this is a summary of what we've just done. Bootstrap the scatter, find all the slopes, take the middle 95%. That's what we just did. Yep? Okay. Okay, so now statisticians and data scientists come around and they're always saying, maybe it's all due to chance. So what is the question here? There is somebody very excited about their regression line, right? They've seen a regression line, they've seen a slope, there's a linear relation between x and y, they're jumping up and down. Okay, along comes the data scientist, who always looks like that. But what if that slope was just due to chance? What if the scatter was sloping just because of the way the points were generated? More specifically, what if the true line is actually flat? Because if the true line is actually flat, there is no linear relation between x and y. And if you're seeing a linear relation in your scatter diagram, it may be just sampling variability. And that is something you have to check out first. Right? Are you seeing something that is spurious because of randomness, or is it actually genuine? And so before we actually go and do that, we know how to do that, but before we go and do that, is the question clear? Let me show you an example where the question actually arises very visibly. And first we'll run our simulation. Okay. So here, look, I'm drawing a true line, and I'm telling it, draw a true line with slope 0. Yes? I'm drawing a flat line and generating points. So this is what we get to see. Here's our estimate. It's kind of negative sloping. And so we draw it, and, well, we're seeing a little bit of something. Right? Let me run it again. Look at that. The true line's flat. Scatter diagram looks like that. We say, ooh, look, positive slope. Draw the two together. We have made an error. Yep. And it's an error that actually is material because the reality is there is no linear relation between the two. But now we're saying there is. So we have to watch for this. And in our example, actually, so this was my reminder to that we are now testing hypotheses. So slope of true line equals 0 versus yes? 0 or not? Okay, so now I want to ask you what we're going to do. We know how to make a confidence interval for the slope. We know how to estimate the slope, right? We're going to say the slope, we think the slope is in this interval. How do you test this hypothesis? You look at that interval, does it have 0 or not? Right? If it does not have 0, then what's your conclusion? You got a null and alternative. You've estimated the true slope with a confidence interval. That interval does not contain 0 in it. Which will you pick? You'll pick alternative. Yep. If the slope has 0 in it, then what? If the interval has 0 in it, then what? Well, it could be the null. Yes, you can't say an alternative. And so we are going to run this. I'm going to show you an example where this arises. If I try to use maternal age to predict birth weight, the scatter diagram looks like that. Right? Now, the slope is positive, but this is highly suspicious. Yep? That kind of looks flat, right? The reality, this is very well worth checking whether the reality is flat. Yep? So what we are going to do is we are going to run our confidence interval for this slope, the slope of the true line. And take a look. The interval is that yellow bit. Where's 0? It's in it. Yep. So you can't conclude that there is genuinely a positive slope. Okay? So that interval has two purposes. It does estimate the true slope, and you can use it to see whether the true slope is 0 or not. Very handy. Now, in the end, what you want to do with when you're given one variable and trying and looking at another is you want to see, okay, so if the next mother walks into the hospital and I know how long she's being pregnant and she's about to give birth, can I estimate the birth weight of the baby? That's what you want to do. You want to predict. So that's the next thing we're going to do is we're going to do some prediction. So that's our original scatter diagram, number of gestational days, birth weight. If the number of gestational days is 300, you agree our one-figure prediction will be just this height right here. Yep? That's our regression line. That's the fitted value. And I'm looking, that's 100 to 150, so that's 125. This thing is somewhere in between 125 and 150. You agree? Okay. If you had to calculate it mathematically, what would you have to do? You would have to find that yellow line. Yes? How do you find that yellow line? The slope and the intercept of the regression line. Yes, you'd get a slope and an intercept. You would do slope times 300 plus the intercept. Yes? Okay, so what I've done is I've written a function that does that. So you have your table, the x column, the y column, and now the given value of x. It calculates the slope of the regression line, the intercept of the regression line, and it returns slope times the given x plus b. That's why I'm calling it fitted value. And so the fitted value is, according to our function, 129, and that looks reasonable for this. We said it was going to be between 125 and 150. Yep? Okay, so we have one prediction. Person comes in, 300 gestational days, we are predicting 129 ounces. Done? Scatter diagram could have been different. This prediction is based on this one sample. So, but it could have been different. How different could it have been? We need more samples. What are we going to do? We're going to bootstrap the scatter diagram, and then we're going to get a regression line through each one. Through each one, there is going to be a prediction at 300. You agree? Then we're going to collect them all. And we're going to take the middle 95%. How about that for a plan? Does that sound like a plan? That sounds like a plan. And I have done it so that you can see it visually. This is the first 10. I can't show you 2,500 lines. Right? It's a mess. So I've just shown you the first 10. We bootstrap the scatter 10 times. We get 10 lines. Here is 300. For each of them, we have an interval. For each of them, we have a prediction. So we get an interval. Yes? And so I have collected all of that in a function called bootstrap prediction. And it is chugging away. It is chugging away. There you go. That's a prediction interval. What just happened there? I didn't show you the function. Everybody went, ah. What happened? How many times did we bootstrap? Can you read this and figure out how many times we bootstrapped? 2,500 times. Right? We took a bootstrap sample 2,500 times. Each time, we got the slope and intercept of the regression line. Yep. And we computed the fitted value at 300. How do I know 300? Because I'm telling it 300 right there. So we got 2,500 fitted values. We drew the histogram of those and took the middle 95%. This is known as a prediction interval. Notice it goes from 127 to 131. Yes? What's in the center of that? 129. That was what we saw with our original line. All clear? How to make a prediction interval? It's just a repeat of the same process. Anything that you can do to get one prediction, you can repeat by the bootstrap to get as many more as you have patience for. And so I want to finish up by showing you what happens when you change this value of x. So I have 300. I'm going to play the same game with 285. What are these, by the way? This is the number of gestational days. How long the woman has been pregnant. Right? She's about to give birth. So we're going to do the same thing for 285. While that is running, I want you to look at the width of this interval. This goes from 127 to 131. That's 4 ounces wide. Agreed? Okay, so keep that number in your head. It's 4 ounces wide, and someday this will stop chugging. And now you have a prediction at x equals at, so 285 days. That goes from 121 to 123. And that is how wide? It is 2 ounces wide. It's a narrower interval. Right? Noticeably narrower interval. And I want to end this lecture with a picture that explains why that interval is narrower. So you are looking at the predictor variable, right? And so let me actually... There's 300. 285 is somewhere here. Yes? Notice that the graph, there's a center here. There's a mean, which is 279. That's somewhere here. 285 is closer to the mean than 300. You agree? So some x's are closer to the center and some are far away. And what I want to see is what happens when we do our bootstrapping. So now what we'll do is we'll bootstrap, and we'll make our predictions using the same lines for both 285 and 300. Okay? And I'm going to show you 10 of those lines. All those regression lines, you expect them to pass through the center, right? Roughly. Right? All of those scatter diagrams are going to have roughly the same center. So near the center, all the lines are going to be close. Far away from the center, the lines flare out. That's what lines do. Right? Where they intersect, they are close, but then they flare. And so the further the point is from the center, and remember the mean was 279, the mean is here. The further the point is from the center, the more variable your estimates are. If I run again, there's just more spread here than there is here. And that is why when you